Welcome students. In this class of quantum mechanics, today's topic is scattering cross section. Now the first topic is scattering by spherically symmetric potential. Scattering by spherically symmetric potential. Now spherically symmetric or a central potential means the potential energy depends only on the magnitude of the distance between the two particles. That is, where the potential V is a function of R1 difference R2. Generally, R1 and R2 are the position vectors of the two particles. Or we can write V equals to some function of, that is, for a central potential or spherically symmetric potential, V can be written as V function R1 difference R2, where R1 and R2 are the position vectors, or it can be written as some function of VR, or since this R is the magnitude, so it can be simplified as V of R. In that case, the time independent Schrodinger equation in that case means where the potential is dependent like this, the Schrodinger's equation, time independent Schrodinger's equation for a particle of mass mu equals to m1 m2 by m1 plus m2. You can recall it as the reduced mass, that is mu equals to m1 m2 by m1 plus m2, and this is the reduced mass. So the time independent Schrodinger's equation for a particle of mass mu equals to m1 m2 by m1 plus m2 moving in a field described by the potential function V of R and is given as del square psi R plus twice mu by h cut square, then E minus VR psi R equals to 0. So this is the Schrodinger's time independent Schrodinger's equation, where capital E represents the energy in the center of mass system. Okay, now since in this class I have to communicate with you via this online medium, so if possible just comment me on the comment section and I will read through this comment section that whether the topic is or whether there are some technical problems within myself and you. So please mention or please comment here. Now at large distance, that is when R tends to infinity from the scattering center, the form of the wave function psi R, that is the solution of this equation 1, should be such that it must consist two parts. Two parts means okay, Shanchari, glad to hear that, no problem. Okay, fine. So at large distance, that is where R tends to infinity from the scattering center, the form of the wave function psi R should consist of two parts. One part is the incident wave function, that is psi INC. INC stands for incident, so psi INC is one part and the other part should be psi SC for scattering. Now, that's why we can write the solution, that is psi r. It can be written as, it must be a function of r theta phi in 3 dimension, and when r tends to infinity, this psi r, that is the solution of equation 1, should consist of these two parts, that is psi inc. Inc means, as I tell, that psi inc is the incident wave function and psi sc is the scattered wave function. And this is called the asymptotic form of the solution of equation 1. Now, let's move on to these two different parts of the solution, that is, firstly, the incident wave function psi inc, and later on we will move on to get the or find psi sc. Now, for r tends to infinity, the incident wave is described. The incident wave is described by, so I must remove this equation 1. Now the incident wave is described by psi inc, that is the incident wave that equals to a e to the power I k z. Now this is a plane wave. This is a plane wave. You can see it from the equation written here, where we have assumed that the wave travels in the positive z direction. Here the wave travels in the positive z direction, and according to the interpretation of the unnormalizable wave functions, mod of psi inc square, that is mod of psi inc square, it is the number of incident particles. It is the number of incident particles per unit volume. This is the number of incident particles per unit volume. Now, if we normalize the wave function psi inc such that the density of particles, why I am telling that density, since psi inc square means the number of incident particles per unit volume, that is, actually it represents the density. So if we normalize the wave function psi inc in such a manner that the density of particles in the incident beam is 1 per unit volume, that is, number of incident particles per unit volume is 1, that means that capital A must be equals to 1. Thus, psi inc, now I have left this psi r. It should be written as equation 2. Okay, just write it down, that psi r, which is a function of psi r theta phi, when r tends to infinity, it becomes psi inc plus psi sc, and this is equation 2. Now, as the number of incident particles per unit volume is the density, and if we normalize psi inc in such a manner that the number of particles per unit volume becomes 1, that means psi inc, or the incident wave function, equals to 1, and it actually means that the value of capital A should be 1. So putting the value of capital A, we get psi inc, that is the incident wave function, is actually e to the power I k z, and let it be equation 3. Now let's move on to the scattering part, as this is the wave function for the incident part. Now, since the scattering is assumed to be elastic, assumed to be elastic, psi SC must have the same propagation constant k. Psi SC must have the same propagation constant k, but it must be a spherical wave as these particles move radially outward in all possible directions. Of course, at a large distance from the target. Now, the direction of any scattered particle is indicated by the polar angles theta and phi, with the z-axis in the direction of in the direction of incident. So the situation looks like this, and in the thumbnail of this video I have actually given this figure in somewhat simplified form. You have to draw this. Sorry, the curvature is, this looks better. Now this is the z-axis, that is the incident direction. Now this one is our target. This one is the target, and this is the cone of scattering at angle theta. Now, what is theta? Now, if the scattered wave is this, so this is the angle theta. Actually, this is the reference plane. This is the reference plane. This is the scattered ray, and from this is the scattering plane. This is the scattering plane. So here one is the scattering plane, the other one is the reference plane. This is the incident ray, O is the target, and the incident ray is in the direction of the z-axis. Now, what I am talking about, that since the scattering is assumed to be elastic, psi SC must have the same propagation constant k, where propagation constant k is actually, we have used it for the incident wave function psi inc, and equation 3, that is our last equation, and it was psi inc equals to e to the power I k z. So psi SC, that is the scattering wave function, must have the same propagation constant k, and it must be a spherical wave as these particles move radially outward in all possible direction, and that's why this cone of scattering is made. Now, the direction of any scattered particle is indicated by the polar angles theta and phi, and actually this is theta, and this is the azimuthal angle phi. This is the azimuthal angle phi. This one is the azimuthal angle phi. Now here theta is called the angle of scattering, and it is the angle between the scattered and incident direction. This is the angle theta, and it is known as the angle of scattering as because it is the angle between the scattered ray and the incident ray. Now these two directions together define the plane of scattering. These two directions, that is the scattered ray and the incident ray, and the angle between these two rays is the angle of scattering, and these two directions made the scattering plane. Okay. Now the azimuthal angle phi specifies the orientation of this plane with respect to some reference plane containing the z axis. So this is the azimuthal angle phi, and it actually represents a reference plane, with respect to the incident wave direction. Now the scattered wave being spherical, it can be written as psi sc. It can be written as psi sc equals to some angle of theta e to the power I k r by r, and this is equation 4. So this is the scattered wave, and this is the representation of the scattered wave, since it is a spherical wave, as because from a large distance from the target, the scattered rays are outward and in all possible directions, that is in all three dimensions. So the scattered wave must be spherical, and it can be written as psi sc equals to some function of theta e to the power I k r by r. And as in the case of a spherical wave, this k and r are in the same direction. Hence, if we find out the dot product of k and r, that is k dot r, if we find the value of k dot r, it actually gives us k, that is the scalar value of k, the scalar value of r, and the angle f theta. Now the function, this is the function f theta. This function f theta describes the angular distribution of the scattered wave. This function f theta actually describes the angular distribution of the scattered wave and is known as the scattering amplitude. What is the scattering amplitude? The function f theta describes the angular distribution of the scattered wave and is known as the scattering amplitude. Now the number of particles. So proceeding further, I have to remove this. I think all of you have drawn this. So the number of particles which enter the collector or the detector placed at r theta phi per unit time would be given by, that is the number of particles which enter the collector or the distributor, or the rather detector, or detector placed at r theta phi per unit time. This value dn should be mod of psi sc square into v ds. This is equation 5, where v is the particle velocity, and ds is the face area of the detector. That is, the face area of the detector is ds. This is the face area, of the detector, face area of detector or the collector. Okay, and mod psi sc square into V, mod psi sc square into V actually represents the flux of the scattered particles, that is number of particles per unit time per unit area, and as you know, this is nothing but the flux. So mod psi sc square into V is actually the flux, of scattered particles, or it can be written as number of particles per unit time per unit area. So this is actually the flux of scattered particles. So the previous figure can be simplified or can be redrawn as, this is the incident beam, this is the incident beam. If this is the target or the scatterer, and this is the face area of the collector, that is, if this is ds, this is the face area of the collector, that is the detector or the collector which actually collects these scattered particles. This is omega, and omega is actually a function of theta and phi. This is z direction, and this angle, this minimum angle or the small angle, is the d omega. Now the above number dn, this number dn, that is the, would be proportional to the intensity I of the incident beam. It is obvious, that is the number of particles collected by the detector or the collector must be proportional to the intensity of the incident beam, and to the solid angle d omega, as because this solid angle actually the angle which is made by the detector or the face area of the detector with the target or with the scatterer. So the number of particles collected per unit area per unit time, that is dn, or the number of particles collected by the detector dn, should actually proportional to the intensity of the incident particles as well as proportional to the angle, that is d omega, and where d omega can be written as d omega is actually equals to ds by r square. That can be written as you know, that it is sine theta d phi. Now the solid angle that is subtended by the collector at the center of force. Okay, so this is d omega. Thus the number dn, is so I have to remove this. So the number dn is actually proportional to the intensity of the incident particles as well as the solid angle, that is d omega, or it can be written as some proportional constant, and this constant is written as sigma of theta into I d omega, or this is sigma theta. Intensity means psi inc square, as because psi inc square is the magnitude or the amplitude, and as all we know that the amplitude square is nothing but the intensity. So this is psi inc square to V into d omega, and let it be equation 6. So mod of psi inc square into V is called the incident flux, as well as since mod of psi sc square into V is the scattered flux. So mod psi inc square into V is the flux of the incident particles. Now, in general, this proportionality constant is actually taken as sigma theta comma phi. But here I am omitting that sigma as because that sigma theta has dimensions of area, and it is called the differential scattering cross section. This is the differential scattering cross section, sigma theta, differential scattering cross section. Now from this equation 5 and 6, from equation 5 and 6, where equation 5 gives us dn in terms of the scattered flux, that is mod psi sc square into vds, and equation 6 gives us dn in terms of the incident flux, that is function of theta sigma theta mod psi inc square into v d omega. And as because left hand side of these equations 5 and 6 are equal, so we can write that is mod psi sc square vds is equals to sigma theta mod psi inc square into v d omega. So so we can write, that is comparing equations 5 and 6, we can write v sigma theta d omega, actually mod of psi inc square v sigma theta d omega is equals to mod psi sc square into v ds. Okay. Now this is actually equation 7. Now let's substitute the value of psi inc and psi sc. These are given by equations, I think, 3 and 4. So substituting the values of psi inc and psi sc from equations 3 and 4 and substituting in this equation 7, we actually get v sigma theta d omega is equals to mod f theta square by r square into v ds. Or as we from equation 6, no, that is not equation 6, but from equation 5, no, that was not an equation where the solid angle d omega is written as ds by r square. So here we can write ds by r square as d omega, and it become mod of f theta square into v into d omega. Okay, so we can cancel this v from both sides, and we have sigma theta is equals to mod of f theta square, or that equals to d sigma d omega, and let it be equation 8. Okay, have you any doubts? Please mention. If you have any doubt, please mention in the comment, or I will proceed further. Have you any doubts? Everything is okay? No doubt, sir. Okay, fine. So let's come to the discussion. Now, in view of this equation 8, f of theta is what we can define it, or what we can call it. F of theta is the scattering amplitude. The total number of particles scattered in unit time, can be obtained from equation 6 by integrating it over all directions. Equation 6, what was equation 6? Equation 6 was dn is equals to sigma theta dn. Equation 6 was dn is equals to sigma theta I d omega. So if we want to find out the total number of particles scattered in unit time, it can be obtained by integrating it over all directions. So we can find it as integral dn equals to integral sigma theta I d omega, and then we find dn becomes n scattering. It will give us n scattering, and as I is the intensity, so it remains outside the integral, and it can be written as I sigma, let it be equation 9, where sigma is called the total scattering cross section, and this sigma, we can find this sigma also. So this sigma is actually integral of sigma theta d omega. Now we can write it as double integral, where phi, that is the azimuthal angle, varies from 0 to 2 pi. So the integral becomes 0 to 2 pi. Then comes the integration limit for theta, and it becomes 0 to pi sigma theta sine theta d theta d phi. And then putting the value of d phi, that is 2 pi, we can actually write it as 2 pi integral 0 to pi sigma theta into sine theta d theta, and let it be equation 9a. Is it okay? Thus, the asymptotic form of solution, now that is the target of our discussion, that is to find out the azimuthal solution of the wave function psi. Thus the asymptotic form of solution of equation 2 becomes psi r. That was psi r, and we want to find out the solution at a large distance from the scatterer, that is from the target. So for r tends to infinity, and we have told that it actually consists of two parts, psi inc and psi sc. Now psi inc becomes e to the power ikz. So remaining this e to the power ikz for psi inc plus f of theta e to the power I kr by r, and this is this is the asymptotic form of equation of solution of equation 2. Okay, so this is the first part of discussion of our scattering cross section, or the chapter scattering starts from this. Later on in my next discussion, I will proceed to the second and the third part of the topic. Actually, these classes are planned to be taken on Thursday this time, and if any changes occur, then I will tell you in the WhatsApp group. But before leave this discussion today, just give your feedback on the WhatsApp group, that whether some informations or some sort of difficulties you faced here, since this is your first interactive class, or I think this is the first experience of this live class. So let it be discussed on the group itself. I'm waiting for your feedback, and my next class should be on Saturday the 10th at the same time, but a different topic. I think I will take your class on photonics on the second in our second class, that is on Saturday at 7:30 p.m. Okay, goodbye.